Good afternoon, everybody. Good morning for those of you west of us. Welcome to this week's Community Zoom. Just a quick update on the status of the observatory before moving on to today's speaker. So, as many of you know, the Green Bank telescope is currently down for repair. We had a damaged wheel. That is moving along nicely. We've identified processes and contractors to do the work. We've refurbished the jack that has to hold up the telescope. We expect that the contractor will be available in mid-February, and that all should happen then in a couple of weeks. That we should get the wheel back on the telescope, and we'll need to do some more testing and inspection. We're also working a bit on some of the telescope foundation. Pouring some new grout. That will also happen mid-February. All going well, we expect to be back on the air early March. So an email went out yesterday to the observers, users, those with active projects. So I'll keep you updated just as soon as we learn about anything. This is all fine. We know what we're doing. This is not a particularly difficult process. It just takes the right equipment and the right people, and we're lining that up nicely. Today is proposal date. The proposals are due today, so please get your proposals in. We're looking forward to looking at the next batch of proposals. If you submitted a proposal for the special call for the low frequency filler time, you should have gotten your disposition letters, and those went out last week. So congratulations, all of those of you who've gotten time, and we will get back on the air and start getting you your data. One last note, our Breakthrough Listen colleagues had a press release last week talking about some of their Breakthrough Listen data analysis. They're applying artificial intelligence to their data. Much of that data, or some of that data at least, comes from the Green Bank telescope. So it was nice to see some of the press that attracted worldwide, and it's a nice story. These artificial intelligence, machine learning algorithms are now being used on the Breakthrough Listen data and identifying some interesting candidate signals. So stay tuned for that. I'm sure if they're successful, you will hear about that through the mainstream media. All right, with that, I'll hand it off to Jay Lockman, who will introduce today's speaker.
Thanks very much, Jim. Our speaker today is Michael Garrett of Leiden University and the University of Manchester's Jodrell Bank Center for Astrophysics. He will be speaking on SETI, near and far. Let me remind everyone that this presentation is being recorded for future viewing, and that if you have questions, we will have a Q&A session at the end of Michael's talk. Please submit your questions through the button at the lower right of your screen. Thanks very much, Michael. Take it away.
Okay. Thanks, Jay. I'll just share my screen. Okay, so hopefully you can see my first slide.
Yes, that looks fine.
Okay, great. So first of all, thanks for the kind invitation to give the talk. I was just listening to Jim there talking about some interesting maintenance on the GBT. It's good to know that all these big telescopes have all these kind of very similar problems, because we are doing exactly the same with the Lovell telescope that you can see on the slide in the background there. I'm not going to talk about that today, but what I would like to talk about is SETI, the search for extraterrestrial intelligence, and in particular, looking for signals that are relatively nearby in our own galaxy, but also thinking about signals that are really much further away, outside of our galaxy. So, extragalactic SETI signals. Just to make sure everyone's on the same page, so SETI as I'm sure you all know, is the search for extraterrestrial intelligence. What does that mean? Well, basically, we're looking for artificial signals that are rather different from the natural signals that we see from stars and galaxies, etc. Signals that have been generated by advanced civilizations. Sometimes we call these techno signatures, sort of signatures or artificial signatures produced by technology. So that's roughly what we're looking for. And of course, the sort of classical example of those artificial signals are narrowband radio signals, the kind of signals that we use to communicate here on this planet. And that hopefully with telescopes like the GBT and with backends like the Breakthrough Listen backend with, you know, very high spectral and temporal resolution, we can have a chance to actually detect those signals. But SETI and technosignature research in general is much wider than that. And I'm not going to talk about that today, but I would like to mention it, that, you know, we're also looking at other parts of the electromagnetic spectrum, also narrowband signals in the optical, which you're probably familiar with, but also in terms of broadband emission, looking at departures from spectral energy distributions of stars and galaxies that might be caused by technology. And the obvious example of that is if you have an advanced civilization that's using a lot of energy, they presumably also produce a lot of waste energy, and that probably is in the form of heat. And so if you look at cosmic objects and you see a bump in the infrared, then where you don't expect to see a bump, then perhaps that's also a signature that there's some advanced civilization there that is essentially kind of corrupting your astronomical data in a sense. So that's SETI. And of course, you know, I think when we talk about SETI to the general public, but even with our colleagues and even when we publish papers, we have a fairly simplified view of what it is that we're trying to do. And that's represented by this figure here. So you have a large radio telescope on one side, and then typically you have a very nearby star, and you're observing that star looking for one of these sort of artificial signals, narrowband radio signals, for example. So that's kind of our classical concept of what we do, and that's what we say we do. That's what we publish in refereed journals about what we do. But we also know that actually radio telescopes are actually a bit different from that. They obviously have a primary beam response. They have a field of view, so that, you know, that field of view, that patch of sky that they're sensitive to can be as large as, you know, a full moon at low frequencies around 1 gigahertz. So we're not really being truthful in a sense when we talk about, you know, observing a single star. When we do SETI, actually, we're looking at especially many background stars in our own Milky Way, but also actually a few faint stars that are in the foreground. And of course, also things which are even beyond our own Milky Way. And for quite some time, it's kind of annoyed me, to be honest, that we're not a bit more upfront about that we're not actually sort of pointing at particular nearby stars. But in addition to that, we're also sensitive to other stars in the field of view, other stars in our own galaxy, and of course, also these background objects. So if you like memes, then this is one that I kind of made up, you know, what people think we do, what we actually tell people that we do. And this is what we really do. We're actually looking out into space. We're looking at foreground stars, background stars within the Milky Way, and actually nearby extragalactic systems are also something that we should, in fact, be considering. So that's what the talk is sort of going to be over the next 10 minutes or so. So we've been able to make actually a lot of progress in this area just over the last few years. And this is a paper that was published in 2020 by a student of ours, Wlodarczyk-Sroka, who unfortunately passed away last year. He was working with myself and Garrett Siemion, who's the PI of Breakthrough Listen. And, you know, for many years, you know, people have realized, of course, that we're not observing just a single star, but many stars. But until the era of Gaia, the ESA mission, we didn't really know the distance to most stars in the Milky Way. And that's still the case, but we know actually billions of distances to billions of stars. And when we look at that patch of sky with the GBT, we actually know the distance to tens of thousands, even hundreds of thousands of stars that are in our field of view. So we can now actually sort of say something about what we're really constraining when we do a SETI observation. We're not just looking at a single star, we're looking at maybe something like 100,000 galactic stars with known distances. So we can actually do much better when we try and estimate what the prevalence is of powerful extraterrestrial transmitters with long duty cycles, so things that are probably on most of the time. We can actually say that something like 0.04% of stellar systems, less than 0.04% of stellar systems within 200 parsec host such transmitters. So we can put sort of upper limits on these figures, which are much better than what we can do when we consider that there's only a single star being observed. Actually, we're observing much more. And when we take that into account, we actually put much sort of harder limits on the prevalence of these transmitters in the Milky Way galaxy. So if you're interested, have a look at that paper. It's also on the archive. Now, going beyond the Milky Way and looking out to the nearest sort of galaxies, galaxy groups, and galaxy clusters, what can we say about those? And you know, can SETI be in some ways sensitive to signals that might be coming from these nearby galaxies and galaxy groups, etc. Well, I was thinking about that about a year ago over Christmas, and one thing I wanted to do was just to kind of familiarize myself with the Breakthrough Listen fields. What do they look like? What do they contain? So I went through all of them, and there's a few thousand of them, 1,500 or so, and I went through them all, just looking at them. And there's some things that you begin to realize about those fields. The first thing is that the stars that are being observed, because they're selected to be really nearby, they're very, very bright. They're so bright, in fact, that Gaia typically flags them. So Gaia finds it difficult to find distances for these guys automatically, just because they're so bright. And you can see that in the figures here. You know, they really saturate the CCD. They're also in multiple systems, typically, you know, binary systems or higher multiples. So they're probably not the best targets in some senses, if you think that, you know, isolated stars are more likely to have planetary systems, etc., etc. But if you go beyond that, you also see that, you know, there's, of course, this is no surprise, but you also see that there are some interesting objects, and some of them are actually relatively nearby. They're extragalactic, but at least in a cosmological sense, they're sort of on our doorstep. So quite a lot of galaxies, nearby galaxy groups, nearby clusters. So you can see a few of these here on the left, and also some things like interacting galaxies that are also pretty nearby there on the right hand side. And then going a little bit further, you also find that there's quite a large fraction of, you know, maybe not famous exotica in the fields, but certainly things that are catalogued in sort of 4C, for example, radio sources, bright radio sources in the fields that you see on the left-hand side there, radio galaxies that almost certainly increase the system temperature of a very sensitive telescope like the GBT. And then, you know, real astrophysical exotica, as we call them in the SETI community, AGN, all flavors of AGN, quasars, BL-lax, even a few of the fields have gravitational lens systems. So that was just to get a feel of what, you know, we have in our field of view when we make these observations with the Breakthrough Lesson program. And what can we actually sort of do with this? Well, why is it interesting in the first place? I think one sort of reason it's interesting to think about, you know, whether we're able to detect signals from nearby galaxies is that they just contain so many stars. So there's so many potential places for advanced civilizations to have arisen within our field of view. And can we use that to sort of further constrain, you know, extraterrestrial transmitters, knowing that these galaxies are in our field of view and they're relatively sort of nearby and they're containing, you know, billions of stars and billions of planetary systems. You know, could it be, you know, although these galaxies are really far away or relatively far away compared to stars in our own galaxy, could there be some very rare but really powerful signals that we could actually detect even at these, you know, really vast distances? Well, you know, it's hard to know. So one thing is that you can look at the kind of, you know, powers of transmitters that we have in our own planet. You can see there cell phones and the cell towers that provide the mobile network. You know, there are billions of cell phones, there are millions of cell towers around the world. So we have many of these. We have much fewer interplanetary radar systems or military radar systems looking for, you know, over the horizon ballistic missile warning systems. So there does appear to be a kind of power law there when you begin to plot these things, and you have intermediate things like airport radar and sort of traditional military radar systems. And it's interesting to think, do radio transmitters in the rest of the universe, do they also have that kind of power law where there's lots of faint things, but still there might just be a few rare, very powerful transmitters out there. It's a little bit like the radio source counts, where we see the same kind of thing, a few very powerful radio sources in the sky, but many, many faint ones. And so, if that's the case, then, perhaps we can actually say something about these sort of potentially rare transmitters and our ability to detect them. So don't worry too much about this diagram, but on the x-axis, you have sensitivity increasing in that direction towards the left. And you have essentially field of view, or the number of potential SETI targets that you're observing simultaneously in your field of view. That's on the y-axis. And if you plot the results that we got from our Gaia analysis of the Breakthrough Listen data in our own galaxy, then that's the yellow squares that you see there on the sort of top left-hand side. And if you then look at some of the non-detections to nearby galaxies that we've also seen from Breakthrough Listen, and which came in our analysis of the extragalactic objects, these are the red sort of data points with the large error bars on the right-hand side. To cut a long story short, it's really telling us, and this isn't really sort of surprising, that if we really want to sort of break into new territory with SETI, we need to go for more sensitivity. But I think in particular, we really need to go for field of view, especially if the signals that we're looking for are quite a bit more powerful, but much, much rarer than we've so far kind of assumed. So getting into this sort of terra incognita is definitely the place where SETI needs to go you know, over the next years and decades into the future. So this is written up also in a paper. This is work that I did with Andrew Siemion. It's published in, I think, September last year. So if you're interested in that, then please take a look at it. And finally, I think Jim already mentioned this, but I wanted to mention it because I think it's really an important result. You know, the application of AI to the breakthrough analysis. You know, I think it's really fantastic what has been achieved there. Detecting 8 very interesting signals, using AI signals that were not detected before, using the sort of traditional human-driven analysis techniques. That's a bit of a game changer for SETI. If we can trust AI to find those kind of signals, then this can really make a huge impact in the field, I think. There's a Nature paper by Peter Ma and colleagues that I guess is out. So it's certainly on the archive, and I guess it's out on Thursday. And there's a couple of articles in the conversation that you might be interested in if you don't want to wade through the Nature paper. I'm also talking about the future impact of AI on the field. So just to sum up, SETI observations. Yes, we need to get away from this simplified view that we're looking at single stars. We're actually looking at many foreground and background stars in our own Milky Way, and we're also potentially sensitive to nearby galaxies and galaxy groups and clusters. And everywhere we look with the GBT or any other telescope is always going to contain also these, you know, astrophysical exotica. You don't need to particularly go out and look for them. You know, they're just always there. And it's time to sort of begin to take this into account. We're working on a galactic model that will allow people to sort of, if they've made a SETI observation of a particular star, to also work out how many other stars they've seen at various distances within the telescope's field of view. We're going to be working on that in the coming year. And finally, you know, especially the work that's been happening in the GBT and Parkes and Meerkat and soon the VLA, the work that Breakthrough have been doing, and the new introduction of AI. Really, you know, there's just never been a better time to look for SETI signals. And it's an extremely exciting period, and it's great to see the GBT being part of that. So I'll leave it there, and happy to take any questions that you might have.
Thanks very much, Michael, for a most fascinating presentation. Let me remind everyone to submit questions through the Q&A boxes, which are to your lower right, and we have a question already. Oh, well, congratulations for a wonderful presentation. And then a question. Earth's communications has shifted from narrowband signals to broadband digital modulations. With a comparable SETI civilization, has detection of these potential SETI signals become significantly more difficult?
That's possibly true, although there are some people that have been working on looking for also the non-random aspects of some of these broadband signals. So again, this is something that AI will be really good at, that humans are probably less good at. So I think it's, you know, what you say is absolutely true, that the 5G systems, for example, are using large parts of the electromagnetic spectrum these days. And so we're no longer just looking or using these very narrowband signals to communicate, but we're actually doing that sort of in the space next to the sort of carrier signals. So it could be a bit more difficult, but it's also the case, and this is something that we're just simulating with the student at the moment, is that if you have a look at the 5G background, that background itself, that broadband background, in principle, if you had a really, really good telescope and you had really, really good spatial resolution with that telescope, you could actually begin to detect that broadband background signal that might be associated with planets, for example. So I think what you say is probably true, but the simulations we've been doing are also extremely interesting. And if you just look at the mobile tower emission coming from our planet, obviously it's orders of magnitude more than the radio emission that we saw before across a wide sort of frequency range. So in some senses, maybe it's a negative, but I think sort of basically going further forward with more sensitive instruments, the fact that we actually use a broadband and they probably use also even larger, broader band might actually be good news for the field.
Mm-hmm. Okay, we have another question that let me paraphrase as asking, are your filters tuned to any particular characteristics of an alien transmitter when you're searching these data?
Well, they're certainly tuned to a certain frequency range. And, as you know, that's roughly for the GBT, that's between typically 1 to 4 gigahertz or so. With parks, it goes a little bit higher. So we're not at the moment. There's not many major SETI surveys that are going beyond those frequencies. And again, maybe, thinking about the previous question, the fact that we know that we are going to much higher frequencies for our own communication purposes means that that's certainly selective. Although, those things are also being addressed also at the GBT, with much higher frequency surveys. So, there is sort of selection. There's also the fact that, if you want to have fantastic temporal resolution and at the same time also fantastic frequency resolution, then you need a lot of space to be able to archive your data, and so a lot of the work that's been done has been done with sort of average data that are averaged up, and we don't maybe know so much about what SETI signals might look like at sub-second temporal sort of resolutions, partly because it's so difficult to store the data for many stars. So I think we are being quite selective. I don't think we're being selective in terms of the types of objects that we're looking at, because although people might be looking at nearby stars that are of solar type class or whatever, the fact, and going back to this whole talk, the fact that you actually have many stars in the field of view, both of GBT, but also of other instruments, the fact that you do have that kind of serendipitous selection of many different types of star with many different types of planet probably orbiting around them. I don't think we're being actually selective. Even when we think we're being selective, we're actually not being selective. We need to remember actually to tell the truth. Sometimes we pretend we're selecting and the central star is selective, but actually all the other stuff around it is just sort of random. It's all the things that you can imagine. So yeah, some aspects are selective, partly due to the data volume, but a lot of other things that people think they're being selective in, actually they're not being selective in.
Just we have time for a couple more questions, and here's one. Can you comment on the new AI detected signals? What are they like?
So I only know what I've seen in the paper, so I'm not involved in the breakthrough lesson data analysis at that level. I've been using their results to do some interesting things, I think. But what I've seen in the journal, to be honest, I thought they looked really good. So to me, they're at least as good as the previous candidate, breakthrough lesson candidate number 1. In fact, some of them to me look better than BLC1. I guess the unfortunate thing is that I think they've had a quick look at those signals or those stars to see if there's still something to be detected, and those narrowband signals have disappeared, so they're not still there, which is unfortunate. But I think we probably come up against that in SETI. In the future we'll see that a lot. That'll happen a lot. I think with interferometers, we can actually do rather better than we do with single dishes, because we can have independent detections on each interferometer arm. And with the introduction of MeerKAT and the VLA, I think even with a single narrowband detection that doesn't repeat, we're going to be able to do very interesting things, because you'll also be able to pinpoint that signal. You'll be able to localize it on the sky with an interferometer. And if you use VLBI, for example, you can actually localize it on the scale of an orbiting planet. So that's going to be really, really, really very, very interesting. But yeah, I think those 8 candidate signals are good. I'm sure Breakthrough Listen will look at them again to see if they've come back. Yeah, no, it's very promising for the future.
I'm afraid that we've run out of time before we've run out of questions, but let me just say that Michael will be able to access these questions, and if they are connected to an email, he'll be able to get back to you with answers. Thanks again for attending, and let me just remind everyone that this session will be available for viewing certainly by tomorrow on the Green Bank Observatory website. Please join us again in 2 weeks on February 15th, when we'll have a speaker from across the other ocean. Antoine Marchal from Australian National University will be talking about mapping the thermal condensations of diffuse hydrogen in the North Celestial Pole Loop. We look forward to joining us then. Thank you.